Okay, class, let's take a look at carrying capacity and what limits population growth. I've intentionally skipped a bunch of math slides. You did a different ed puzzle that looked at those. So in this set, we're really looking at factors that cause the stopping of that exponential growth and when those occur and how we can label them. There's going to be a couple different ways that we label these limiting factors, right? So first up is just general concepts of what major limiting factors are. Habitat loss, land use, habitat destruction. So it may still be there, but it's not at a usable quality. And habitat degradation, that's the usable quality. So loss of wildlife habitat due to misusing it, and a decline in wildlife population because the quality of the habitat has been reduced. So a lot of habitat land-based factors here. Then we have these events that are often human occurrent, but not always, that we just couldn't help. We didn't want to have a major tanker oil leak. We didn't want to hopefully start a forest fire, right? Overpopulation, which generally happens when they had a really good season or breeding season or event, and then their food declines and we get a crash. Humans and hunting can be limiting factors, our ways of controlling the population. And then, of course, we limit properly. There's always good techniques to manage populations, especially if we know that we've been the reason why their natural predator isn't there to manage them and to keep their numbers down. Or we introduced them and now we're trying to keep this problem from going to exponential growth of this problem species. There are, of course, natural reasons why populations are going to experience a loss, and they need to have loss. You can't constantly have that exponential growth like we've talked about, right? There's this limiting. And when organisms get old, they're more likely to be consumed by somebody else. They're more likely to get sick. They're more likely to not digest their food properly. They're more likely to get cold and have weather-related then infections, disease, pneumonias. Population loss occurs if there's too many predators that are then consuming them. That predator-prey relationship gets off in some way, then, or just normal, it's going to cause deaths, and that's okay. Pollution, especially when we look at our waterways, plastics, and acidic levels rising in our oceans, causes a lot of population loss. But so some of that isn't completely natural. Health concerns are always going to cause a decline in the population. Disease, intentional or unintentional, is going to cause a reduction in population. Malnutrition and parasites. So a factor that causes a higher mortality or reduces birth rates is often considered density dependent. It limits the population in a direct relationship to how many are already in the population. Often this works with the more densely packed this population is, the more likely it is that this factor can cause a problem. Disease is going to spread more rapidly when you're close together. And that's been a rule before COVID, right? The more densely packed you are, the more likely you are to share disease. We also recognize that the more population there is, the more food they need. So that's a direct relationship. But there are density-independent factors that the organisms can't control. Weather events, rock slides, major flooding. These are things that the animals, we put a road there, we caused destruction to their habitat. Those are factors that didn't matter if there were 2 or 2 million of that species. Another way to look at limiting factors is extrinsic and intrinsic. These are still factors that are controlling the increase and decrease of a population, just a different way of grouping them. External factors tend to be density independent, right? All those density independent factors are grouped as external or extrinsic. They occur whether or not there were 2 or 2 million. And Wildfires, mudslides are examples of that. Density dependent can kind of vary if it's extrinsic or intrinsic. The quality of the food around is, going to be density dependent. Bad season, too much rain, too much sun, not enough rain, the herbivores aren't going to have food to eat. If they have limited shelter or cover due to humans, due to deforestation, right, they're going to have less places to build homes. If they're competing with overlap in their niche, then we're going to see that is an external competition taking place. Disease, outside of like when we looked at the bighorn sheep that was brought in by the cattle that used that land, right? Hunting and trapping, these are all density dependent. They were going to be there or not if there were a few in the population or a lot, but they occur outside of the organism. Internal or intrinsic factors that create that increase of a population and then a decrease in a population are much more genetically based. So how many offspring they have and how frequently. Intrinsic. How long they live. How they decide their habitat. And how they go about creating that social structure. If they fight to the death, then they just reduce their population number, right? If their behaviors are in such a way that they fight for territory but they allow the other to live, then they're not reducing that number in some way. There's a lot of genetic variability that needs to take into account this. Some birth rates, some organisms are better at maintaining and having young and keeping them alive than others, and those are factors that are intrinsic. So there's always this question of, well, is the population really balanced? If you really look at it, depending on the species, there's always this increase, decrease, increase, decrease. Well, maybe that is a balance of this ebb and flow that exists, because equilibrium doesn't need to be static. It's often dynamic, which means constantly in a flux or change. So that's kind of some of this argument, right? There's never a constant, but there's always this trend we seem to be able to find. And when we don't see a trend, we can often pinpoint the event that caused the change in the trend. So the most common study, again, we're back at that Isle Royale, is the wolf moose predator-prey population of this mostly self-contained island. It's only not self-contained about 10 to 30 days a year when there's an ice bridge between the mainland and this island. And even that, in more recent years, has started to decrease. So we recognize there's this predator-prey relationship that helps create that carrying capacity level for the moose and the wolf. And that has impacts on other parts of the ecosystem. But without one, okay, without the moose, the wolves go extinct. Without wolves, the moose population gets too strong. They eat all their food supply, and then they start to die off too, because they overgraze, right? So if moose levels drop, the wolf population would be much greater. Risk of dropping as well, because that's their food. So it's this constant delayed balance that we see. If the wolves went extinct, the moose population would skyrocket, but then it would eventually reach a limit again, because there's only so much food for the moose. So it would still balance out somewhere along the way. So it's this really dynamic balance that's maintained, right? And the last piece we're going to look at is just a recap, really, of another way of looking at R selection versus K selection theories. And we've already kind of talked about this. R selection is a population that grows rapidly. It grows in really unstable conditions and environments, and it has to put out a lot of young and then expect there to be none for maybe a period of time again, and then put out a lot of young and then none for a period of time again. Right? These populations often start out well below the carrying capacity and then skyrocket to that exponential growth. Our K selections are our stable environment species, are organisms that are pretty predictable in how they grow and develop. And then we have just a chart that kind of gives you that overview of our selected populations and the characteristics we see in them versus our K-selected populations and the characteristics we're going to see in them. And we had looked at this one once before, but I just wanted to come back to it again because this looks at it as another way of looking at like opportunistic versus equilibrial, balanced, right? We already talked about our R-selected tend to create that exponential growth curve. Our K-selected are our logistic growths. They carry around that carrying capacity, they're leveled off. So I hope we've kind of given you a really good overview and understanding of a lot of the population concepts and terms. We are going to look at some predator-prey relationships, not predator-prey relationships, some predatory birds, and look at our raptors and some of their understanding in population growth. And then we'll be wrapping up this unit and we'll test before the end of the trimester.